You. You're one person on a planet of over 8 billion people. Our planet orbits a star. That star is just one of an estimated 100 to 400 billion in our galaxy. And our galaxy? It's just one of an estimated 2 trillion galaxies in the universe. The scale of all of that is, well, it's insane. The entire observable universe is 93 billion light years across, but hold on, that number makes no sense. We're told the universe is 13.8 billion years old. So how can it possibly be bigger than 13.8 billion light years? It feels impossible. And that impossibility is exactly what we're going to figure out today. To even try to wrap our heads around the size of everything, we have to start small. With us, the average human is somewhere between 1.5 and 1.8 meters tall. It's a scale we get. Our homes, our cities, the distances we walk, it's a world built for us. Now, let's zoom out. We're on the surface of the Earth, a giant sphere almost 13,000 kilometers in diameter. If you could drive a car at 100 kilometers an hour without ever stopping, it would take you more than 16 days to circle the equator. That already feels huge. We feel like tiny specks on this vast planet. But in the grand scheme of things, our world isn't vast at all. It's barely the starting line. Let's take one step off our world. Our nearest celestial neighbor is the moon. In pictures, it looks like it's right next door. It's not. The average distance to the moon is a staggering 384,400 kilometers. That number's so big, it's hard to even picture. So let's try this. You could fit 30 Earths side by side in the gap between us and the moon. 30 entire worlds. The Apollo astronauts, the fastest people in history, took about 3 days to make that trip. That car of yours? Driving non-stop, it would take over 5 months to get there. 5 months of watching the Earth shrink behind you, from a marbled sphere to a tiny blue dot. And we've barely even left our cosmic driveway. Okay, now the scale starts to get truly mind-bending. Our car analogy is already breaking down. We need a new unit of measurement, the speed of light. Light moves at a ridiculous 300,000 kilometers every second. It takes light just over a second to get from the moon to us. So, we can say the moon is about 1.3 light seconds away. Let's use this new cosmic yardstick to go further. At the center of our solar system is the sun, about 150 million kilometers away. Light takes 8 minutes and 20 seconds to cross that distance. That means if the sun suddenly vanished, we'd have no idea for over 8 minutes. We'd still see it shining, feel its warmth, completely oblivious, but our solar system is way more than just the sun. The farthest planet, Neptune, orbits at an average distance of about 4.5 billion kilometers from the sun. Light takes about 4 hours and 10 minutes to travel from the sun to Neptune. Beyond that is the Kuiper Belt, and then the Oort cloud, a massive theoretical sphere of icy objects that marks the edge of the sun's gravitational influence. This cloud is so big that it might take light 1 to 2 years just to cross it. 1 light year. That's nearly 9.5 trillion kilometers. Our solar system is so vast that light itself takes years to cross it. And we're about to see how small that truly is. Let's get a faster ship. The fastest thing humanity has ever built is the Parker Solar Probe, hitting a top speed of 690,000 kilometers per hour. Let's point it at the nearest star to our sun, Proxima Centauri, which is 4.25 light years away. How long would our fastest probe take to get there? Somewhere around 6,700 years, an unthinkable amount of time. Entire civilizations would rise and fall, and that tiny probe would still be coasting through the blackness, not even close to its destination. This is interstellar travel. The space between stars isn't just an empty area. It's an ocean of nothingness so profound that our whole solar system is just one tiny, lonely island. So the distance to the next star over is almost comically huge. Now, let's zoom out again. Our Sun and Proxima Centauri are just 2 stars out of billions, all held together by gravity in a colossal structure, our galaxy, the Milky Way. How many stars are in it? The best estimates range from 100 to 400 billion. Let's just say 200 billion. For every person who has ever lived, there are at least 2 stars in our galaxy alone, and many of them have planets. The numbers start to lose all meaning. The size? The Milky Way's main disk is about 100,000 light-years across. If our entire solar system was the size of a single coin, the Milky Way would be the size of North America. That 7,000-year journey to the next star? That's taking one tiny step. When you look up at the night sky, every star you see is in our galaxy, that faint milky band stretching across the sky. That's you looking toward the dense, bright center of our own galaxy, seeing the combined glow of billions of stars. Our solar system is out in one of the spiral arms, about 27,000 light-years from the center. We're in the galactic suburbs. It takes our sun about 250 million years to make a single trip around the Milky Way. The last time we were in this spot, dinosaurs were just starting to roam the Earth. This must be it, right? A galaxy of 200 billion stars, 100,000 light-years wide. This has to be the grandest scale. Nope, not even close. The Milky Way isn't alone. It's part of a small cluster of galaxies called the Local Group. This includes our bigger neighbor, Andromeda, about 2.5 million light-years away. By the way, it's hurtling towards us, and our 2 galaxies will collide and merge in about 4.5 billion years. Now zoom out again. The Local Group, itself millions of light-years across, is just a tiny piece of an even bigger structure, the Virgo supercluster, which contains over 100 other galaxy groups and spans 110 million light-years. And even that isn't the end. In 2014, astronomers realized the Virgo supercluster is just one arm of our true cosmic home, the Laniakea supercluster. Laniakea means immense heaven, and it fits. It's 520 million light-years in diameter and contains around 100,000 galaxies with the combined mass of 100 quadrillion suns. All 100,000 of those galaxies, including ours, are flowing toward a single point called the Great Attractor. At this scale, entire galaxies are just specks of dust. So let's take the final zoom. What does the universe look like on the largest possible scale? It's not just a random scattering of galaxies. It's a magnificent, intricate network of galaxy filaments and walls surrounding vast, nearly empty regions called cosmic voids. This is the cosmic web. The superclusters are the bright knots in this web, and the filaments are the threads connecting them. It looks almost like a brain's neural network. We are now looking at the universe on a scale of billions of light-years. We're seeing light that has been traveling toward us since before the Earth even existed. The further we look, the further back in time we see. And this brings us to the edge, the absolute limit of our vision. Because the universe has a finite age, there's a boundary to what we can see. Light from beyond a certain distance simply hasn't had enough time to reach us. This is the edge of the observable universe. And this is where we get that final, mind-shattering number. The distance from us to that edge, in every direction, is about 46.5 billion light-years. That gives the observable universe a diameter of 93 billion light-years. And this is where we have to hit the brakes. I just told you 2 things that sound like they can't both be true. Fact 1. The universe began 13.8 billion years ago. Fact 2. The part of the universe we can see is 93 billion light years across. Wait, what? How is that possible? If nothing can travel faster than light, then the absolute farthest anything could be from us is 13.8 billion light years. The diameter shouldn't be more than 27.6 billion light years. A diameter of 93 billion light years seems to break the most fundamental rule of physics. Did Einstein get it wrong? Is the Big Bang Theory a bust? The universe is way, way bigger than it feels like it should be. This is one of the biggest points of confusion in all of cosmology, but the answer is one of the coolest things you'll ever hear. The key is understanding what's actually expanding. It's not that galaxies are flying through space away from each other, like shrapnel from a bomb. It's the fabric of space itself that's stretching. Think of it this way. Imagine you have a long, stretchy rubber band. Draw 2 dots on it. One is our Milky Way, and the other is a very distant galaxy near the edge of what we can see. Now, an ant starts walking from the distant dot towards ours. That ant is a photon of light, and it always moves at the same speed. The ant starts its journey. But as it walks, we stretch the rubber band. The space between the dots is expanding. Our little ant keeps walking at its constant speed, but the finish line is getting further and further away. Now, let's apply that to the universe. 13.8 billion years ago, a photon of light was emitted from a galaxy that was, at that moment, much closer to the spot we now occupy. That photon began its long journey toward us. For 13.8 billion years, it traveled at the speed of light. But during that entire time, the space between our location and that galaxy was expanding. So while the photon traveled a distance of 13.8 billion light years through space, the galaxy that sent it was carried much, much further away from us by the expansion of space. Today, when that ancient photon finally hits our telescopes, the galaxy that sent it is now a staggering 46.5 billion light years away. So, did anything break the speed of light? Nope. The rule is that nothing can travel through space faster than light. But there's no limit to how fast space itself can expand. The galaxy wasn't speeding. The universe itself was giving it a ride. What could cause such a massive expansion? Scientists have a theory for this, and it's truly wild: cosmic inflation. The idea is that in the very first fraction of a second, after the Big Bang, a trillionth of a trillionth of a trillionth of a second, the universe underwent a period of insane exponential growth. In this flicker of time, a region of space smaller than an atom might have been stretched to a size larger than a galaxy. This initial, hyper-fast expansion supercharged the growth of the universe, setting the stage for the slower expansion we see today. And it's important to remember, the observable universe isn't the entire universe. It's just the part we can see. The total size might even be infinite. We've seen that the universe isn't just big. It's structured, complex, and expanding in a way that messes with our intuition. We live on a tiny planet, orbiting an average star in the suburbs of a galaxy that's just one of 100,000 in a supercluster, which itself is just a bright spot in a vast cosmic web. We learned that the paradox of the universe's age versus its size has a beautiful solution. Space itself is stretching. The edge of our universe isn't a wall, it's a horizon in time. But the most incredible part of this story isn't the scale. It's the fact that we can even understand it. We are collections of atoms, forged in the hearts of long-dead stars, living on a small rock for a brief moment in time. And yet, through science, we have managed to piece together the story of the cosmos. We have looked out into the darkness and found our place in this grand, unfolding story. And that is perhaps the most insane and most wonderful fact of all. This whole journey, from a single person to the edge of reality itself, is a lot. It's a perspective that can make you feel both incredibly small and part of something magnificent. If you find this stuff as fascinating as I do, think about subscribing. We explore mind-bending topics like this all the time. And let me know in the comments, what cosmic mystery should we unravel next?